Okay, hello everyone, welcome back. We have been talking about the B plus tree as well as the Btree in the previous lectures. For the B plus tree, given a search key, right, we want to do search for the tuples matching the search keys. The search process is like we go from the root and we're going down by comparing the search key versus the keys in the nodes, and we're going down until we reach the leaf nodes, and we can have access to the pointers pointing to the concrete tuples matching our requirements, right? This is a B plus tree. So you see the search process in the B plus tree may require the traversal inside the tree from the root to the leaf nodes, so we can have access to the pointers. And we also discussed another tree structure, it's called Btree, right? So the Btree improved the B plus tree by putting these tuple pointers inside these internal nodes as well. So for all the nodes in the Btree, they have two different kinds of pointers, either pointing to the children nodes or pointing to the concrete tuples in the database systems. And if we want to do a search in the Btree, the process will be very similar. However, we can have access to the pointers to tuples in all the nodes inside the tree. Now, for example, if we want to search for the 65, we can have access to the pointer from the root node directly, right? So you can see from these two different data structures, B plus tree and Btree, if we plan to search for some tuples matching the search keys, the process is now traversal inside the tree, right? Either from the root to the leaf nodes or for all the nodes inside the trees. So this can be very efficient if this tree is very shallow. However, in the real world, if we have a tree which is very deep, and the time cost for traversal inside the tree can still be very, significant. And we may wonder if we have any other options besides the tree structures for maintaining the index table in database systems. The answer is yes, we can have another option, it's called hash tables. I hope you have known about hash tables before, right, in the data structure or the discrete mathematics courses. So formally, a hash table is like a function. Given a search key input, we can map the search key directly to some bucket with the pointers pointing to these data tuples directly. So the hash process is very fast compared with the tree structure. The hash function can be very efficient, especially for large size index tables. So format the hash table is a secondary storage hash table. They are much like the main memory ones. And we have some basic information about hash tables here. I think you have known about this in the discrete mathematics courses. So given a hash table, we have some basic information and properties. First of all, we need to have n buckets. Buckets is like a storage space. Inside it, we can put some like a key as well as pointer pairs. It's very similar to the nodes we have before. We have both key and pointers, but here we have the n buckets. Inside each bucket, we have a bunch of key pointer pairs in them. Beside the buckets, we also have a hash function, which is very important for hash tables. Hash function like this is a mapping. Given some keys, we can map this key to a certain number, now in the range from 0 to n-1. So given any such keys, we can project them to the n buckets, the index of the buckets this key should belongs to. In other words, for the hash tables, we don't need to do the traversal for the search, right? We don't need to traverse from the root to the different nodes, and we can use this hash function, to help us project the keys to this bucket ID directly. And inside each bucket, we have a pointer pointing to concrete data tuples with a key, a k. So in the hash tables, we have a bucket each corresponds to a block, and we also use some overflow blocks when needed, especially if we have some inside this bucket we have so many key and pointer pairs should be stored in them. If it exists a storage space, we can use some overflow blocks to help us. We'll discuss about this later. So you can follow me, right? So for the hash table, we have the basic components. First part is the n buckets. We have a hash function. This hash function can project keys to the bucket IDs from 0 to n-1. And inside the bucket, we have both key as well as pointer pointing to the records or the data tuples with this key. So this is about the hash table. And I can provide you with an example of a hash table. So according to the previous page, the hash table has a bunch of basic components. The first part is about buckets. In this example, we have a bucket. We have a bucket with 0 to 3. In other words, we have 4 buckets. And inside each bucket, we have some storage space. In this example, each bucket can store 2 keys as well as 2 pointers. So this is one bucket. In this bucket, we have 2 storage space. The first part can store 1 key as well as 1 pointer. The second one can also store 1 key and 1 pointer, even though right now it is blank. And this one is also one bucket with 2 storage space, 1 key, 1 pointer, 1 key, 1 pointer, similar for the others. This bucket for this example. How about the hash function? In this example, the keys we have are some chars, either E, B, F, G, A, C, right? These are the chars as such keys. And through the function, they can project these chars or such keys to some bucket ID from 0, 1 to 3. This is the hash function we have. This hash function is predefined in this example. Given a char, we can project it to a bucket ID. Now, given E, we can project it to the bucket 0. Given B or F, we can project it to 1. Given G, we can project it to the bucket 2. And given AC, we can project it to the bucket 3. This is the hash function in this example. Besides this, we also have the pointers in the buckets for each entry. If we have one pointer pointing to some concrete tuples, right now we didn't show the pointer here. There should be a pointer pointing to some tuples or records in our database systems, similar for the remaining ones. So given the hash tables, if we want to search for some chars and we want to find some tuples matching our requirements, for example, if we plan to search for some data tuples with char with a key equals to G, the search process is very fast. Given the search key G, according to the hash function, HG equals to 2. In other words, we can go directly to this bucket number 2 here. So we can go over the entries inside this bucket, and we can access a pointer in the entry matching G directly. So you can see the difference, right? For the previous Btree, we have to do the traversal from the root until we reach the leaf nodes. However, for the hash tables, given a such key, we can go directly to the entries with a pointer, right, via the hash function. It's very fast. Now, if we plan to search for some entries with such key equals to A, the process is like this. We use a hash function. We compute HA, we know it equals to 3, right, according to the previous hash function definition. We know this entry with such a key equals to A should be stored in the bucket number 3. And then we can read the bucket number 3 from the hash table, and we can find it in the first disk or the first entry. We can have access to this entry, also access the pointer, right? Via the pointer, we will be able to get the data tuples matching such key equals to A. So this is such a process with hash tables.